talk a little more about determinants. So we went through this one. By the way, this is called the rule of Saris. There's quite a few rules. There's a Gaussian rule, and there is, I don't know, Bernoulli's or something. There's all tons of ways to find determinants of matrices. This is just the one that I've always gone to. It's been kind of my go-to. But you can also break them down and do some other sort of ways that you can look up. I'll leave it as an exercise for the interested student. So, okay, so let's look at applications. A couple quick go-to applications that where this is really going to be handy and helpful. One is finding the area of a triangle, so if you know where the vertices are, and the other one is to find the area of a parallelogram. And a third one we could also do is the area of a parallelepiped, which is a cube, but like a paralleled, like a parallelogram in three-dimensional shape. Okay, so let's start with the area of a triangle. So we know from life, area of a triangle is 1/2 base times height. Now, if I were to have, we know this, right? 1/2 base times height, that's gonna be proven, no big deal. But if I have a triangle on here that is kind of clean and pretty like this, if I know this, if I know the vertices and this, I could calculate that distance. We can call that h, and we can call this the base. We could readily go ahead and calculate the area to that triangle. Let's up it a little bit. And what if we had a triangle instead that was, I guess you could say crooked? What if it was something like that? Okay. That's not 90 degrees. But if we have a triangle like this, trying to figure out its area is going to be a little more challenging. You would have to, at least I would, my approach, I'd probably go ahead and find the lengths of the sides and then use the law of sine to find the angles. And I'd be able to, there's our law cosine to find the angles. That'd be kind of ugly. We could do it. And I think we have done it, but it's ugly. So instead, we can go ahead and use determinants. Not going to prove it to you, but I will show you that it works. The proof to some of these are pretty exhaustive, pretty big. So let's take this. Let's start with a triangle. The coordinates are -2, 2, 1, 3, and 3, 0. Let's just graph that really quick. So, -2, 2, that, 1, 3, something like that, and then 3, 0, something like that. And see that none of these are really clean and pretty. I'm not on the horizontal or the vertical or anything like that. I don't know if I have any 90 degrees in there. I'd have to do some math to figure that out. But this is where determinants come in. It shows that the area of a triangle, and I'm going to do it over here. The area of a triangle is 1/2 of the determinant of the coordinates. So we'll call this A, B, C, D, E, F. Now, we can't do the determinants for a rectangular matrix. It has to be square, and these ones are going to be 1. Okay, so the area of a triangle using determinants is 1/2 times the coordinates with one column vector. Okay, the coordinates, the points here, this would be, doesn't matter which one, this would be like A, B, C, D, E, F, okay? It doesn't matter which one's where, but it does matter that you keep them ordered pair like that. So A, B, C, D, E, F. Okay, so let's take a look at this one. I'll put the numbers in, I don't need to. So my area, triangle, 1/2, negative 2, 2, 1, 1, 3, 1, 3, 0, 1. Now we need to do the determinant of this matrix over here, of this guy here. So to do that, we'll go ahead and put these first two columns back over here. Negative 2, 2, 1, 3, 3, 0. And now we will use the diagonals. So we're going to have negative 6 plus 6 plus 1 minus 9 plus 0 plus 2 negative 6 plus 6 is 0, 1 minus 9, 10, 11. Oh, hey, this is a 0. That's a 0 right there. There we go. Typo. Okay, so my determinant for this matrix is minus 11. So let's call this, my determinant's minus 11, and my area of my triangle is 1/2 of that. And so area of triangle is 1/2 of negative 11, which is negative 5.5. We done? No. Can you have a negative area? No. The area of a triangle is the absolute value of this. So I really need to go back to this guy here. I need to really put a absolute value around this, okay? Like that. So then my area instead is 5.5. Okay? So the area of this triangle right here with these coordinates is 5.5 units. I will leave it as an exercise for interested student to go ahead and do that using the distance formula and log cosine. Okay, let's do another one. Okay, let's do another one. This time we're going to look at parallelograms, the area of a parallelogram. Okay, so and we're going to do this with vectors. So if I have a coordinate system, set of Cartesian coordinates, and I have some vectors on here. We'll do that vector, and we'll do that vector. This one a little shorter. Okay. And we can call this U and V. Okay. These vectors, I can make them into a parallelogram. So I'm going to do is this guy here. Let's see, something like that, right? Okay, so U, V, again, U and V, here's my parallelogram. The area of this parallelogram is going to be the determinant of U, X, U, Y, V, X, V, Y. Okay, again, absolute value, because I know that this vector is also V, X, comma, V, Y, and this one up here is U, X, comma, U, Y. Okay. And I'll tell you right now, it doesn't matter which vector you put first. Okay. In this case, I just did U and V. I can go V and U. It doesn't matter. Just needs to be in columns. Oh, I think we talked about that a couple of days ago. We talked about the column vector. This is now a column vector. Okay. So let's throw some points on here. Let's call this one, let's see, how about 7 and 2? And we'll call this one 5 and 9. Obviously 0, 0. And we can call this one up here 12, 11. So we can do all of those points. And the only points I care about, only ones we care about are these guys right here. That one and that one. So a parallelogram starting at 0 with these two vectors, we can solve the area by doing this. So let's go ahead and work that out. 5, 9, 7, 2. Okay. 5, 9, 7, 2, UV. And so it's going to be 10 minus 63 is negative 53. Okay. Make sure I got the right points in there. Yep. I got negative 53. Again, absolute value. And there you go. 53 is my area of that guy. Okay. If you want to get crazy, you can do this also with 3 dimensions. So if I had a shape, I don't even know how to draw this, right? So if I had my 3 axes here, and somewhere on this surface, in this plane, this 3-dimensional here, is we had something like this, right? Wow, that's kind of ugly. Let's see if I can redraw that a little cleaner. What if I had something like this? That's the front face, and something like that. And let's not forget this back one. Okay. The reason I was careful to draw all of these is I have 3 vectors. 1, 2, and a 3rd vector back here. Okay. So the area of this guy here is going to be, let's just call this W, you see UVW, UVW, okay, so UVW, that's going to be X. Okay, you can see these are the 3 components of the U vector, the V vector, the W vector. Between those, we can go ahead and figure out the dimensions, or no, sorry, the area of this guy here. Okay, so determinants, pretty powerful, and we can do area through the triangle, or area of a parallelogram using vector notation, or area of a parallelepiped using the determinant, using the x, y's, and z's coordinates.